We're constantly hearing about these massive AI models that are changing the world. But what happens when you need to take that incredible intelligence, that giant, powerful whale, and somehow fit it inside a device the size of a goldfish bowl? Well, that's the whole challenge of Edge AI. And this is the blueprint for how it's actually done. We're going to break down the strategy that makes it all possible. To really get a sense of just how big this problem is, look at this number. By the middle of 2026, we're looking at over 30 billion connected IoT devices out there in the world. That is an absolutely staggering number of tiny computers in our homes, our cars, our factories, all just waiting to get a whole lot smarter. So yeah, these devices are everywhere, but they're small. They have limited power, limited storage, and that leads to the big question, right? How in the world do you get a sophisticated, power-hungry AI to run right there on the device itself without needing to call home to the cloud for every little thing? So here's our game plan. First, we'll lay out the core problem, the Edge AI dilemma. Then we'll get into the secret sauce, the TinyDocker strategy. After that, we'll see how to optimize for the hardware itself, solve the tricky architecture puzzle, and finally, we'll talk about the massive job of managing a whole fleet of these smart gadgets. All right, let's dive into that first piece, the dilemma. For a long time, the answer to any heavy-duty computing was simple. Just send it to the cloud. But you know what? For a growing number of really critical jobs, that's just not good enough anymore. In fact, it's becoming a huge liability. I mean, just think about it. If a surgical robot is making a tiny incision or a self-driving car has to slam on the brakes, you absolutely cannot afford to wait for a signal to travel hundreds of miles to a server and back. The intelligence has to be right there, local and instant. A tiny bit of lag isn't just an inconvenience, it's a catastrophic failure. And here is the technical nightmare in a nutshell. A standard AI development environment, with all the tools and libraries, can easily chew up 8 gigabytes of space. The problem, that tiny little IoT device it needs to live on might only have 16 gigs of storage in total. The development kit itself is taking up half the room before you've even moved the AI model in. It just doesn't fit. So how do you solve this impossible puzzle? The answer is this really clever workflow called the TinyDocker strategy. It's all about being incredibly smart and incredibly efficient with how you package everything up. The magic behind this whole thing is a technique called a Docker multi-stage build. The best way to think about it is like this. Imagine a huge, messy workshop filled with heavy-duty tools. You use all that machinery to build one beautiful, perfect little chair. But when you're done, you don't ship the customer the entire workshop, right? No, you just ship the chair. This process does exactly that, but for software. It's a really simple two-step process. First up is the build stage. Here, you use a big, heavyweight software package with all the compilers and fancy tools you need. This is where you do all the hard work. Then you move to the final stage. And here's the trick. You take only the finished, optimized AI model and you copy it into a tiny, bare-bones image. All those heavy tools, they get left behind in the workshop. And the result? It's just wow. We're talking about AI packages that start out as a totally unmanageable 6 gigabytes, getting shrunk down to a lean, mean 200 megabytes. That is an insane reduction in size, and it's how you really do it. It's how you fit that whale into the goldfish bowl. Okay, but shrinking the file size is only half the story. To get the absolute best performance on a tiny device, your AI model can't just be small. It has to be custom-tailored for the specific computer chip, the silicon, that it's running on. This is kind of like tuning an engine for a specific race car. If your device is running on an NVIDIA chip, for example, you'd use a tool called TensorRT. If it's an Intel chip, you'd use something called OpenVINO. Each of these tools takes that generic AI model and essentially rebuilds it, optimizing it to use the unique strengths of that specific piece of hardware, squeezing every last drop of performance out of it. All right, so we've shrunk the model, we've tuned it for the specific hardware, but there's another trap people fall into all the time. The computer you build everything on is often totally different from the little device you're sending it to. This is what's known as the architectural schism. Your laptop, it probably runs on an x86 architecture. But a lot of these little IoT devices, like a Raspberry Pi, they run on ARM64. They basically speak different languages at a fundamental level. Trying to run code from one on the other is like trying to play a Blu-ray in an old VCR. It's just not going to work. So the solution here is this really slick tool called Docker BuildX. The best way to think of it is as a universal translator.
It lets you, sitting right there at your laptop, build different versions of your AI for all the different architectures at the same time. Then, when that little IoT device asks for the AI, it automatically gets the version that was built specifically for it. This just erases a massive headache and lets you support a whole world of different devices.
Okay, so let's zoom out for a second. Getting one device up and running is awesome, but what happens when you need to manage 1,000 of them? Say in a fleet of drones or a global network of smart sensors, the problem completely changes. And this is a really fundamental shift in how you have to think. You see, deploying a single AI is a technical puzzle to solve, but deploying and maintaining an entire fleet of them, that is a huge strategic and management challenge. It's a whole different ballgame. All of a sudden, you're not just a developer anymore. You're a fleet manager. You have to be watching the CPU and the temperature on every single device to make sure nothing overheats. You need absolutely rock-solid security to stop someone from hijacking your hardware. And you have to deal with version control, making sure every device gets updated correctly as your AI model learns and evolves. And this really cuts to the core of it all. Looking forward, being a top-tier AI developer isn't just about how well you can train a model in a lab. It's about mastering the art of packaging and deploying that intelligence safely, efficiently, and at scale into the thousands of little devices that make up the real world. You know, it's one thing for an AI to seem smart in a simulation, but after seeing everything it takes to shrink it, tune it, and deploy it across a whole fleet, it makes you ask the real question: is your AI actually ready for the real world?